Tonight, we're going to confront one of the strangest truths in all of physics. Empty space is not empty. You've been told that if you remove every atom, every particle, every speck of matter from a region of space, you'd be left with nothing, a perfect void, total emptiness. But that's wrong. Modern physics has revealed that even in the most perfect vacuum imaginable, something remains. Something you cannot remove no matter how hard you try, no matter what technology you use, no matter how much energy you spend. It's always there, filling every point in the universe, and it's responsible for every particle that has ever existed. These are quantum fields, and once you understand what they are and what they do, you will never think about empty space, about matter, or about reality itself the same way again. Before we go any further, if you find this kind of deep exploration fascinating, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with something that seems obvious: emptiness. You know what empty means. An empty room has nothing in it. An empty glass has no water. An empty box holds no objects. You understand this instinctively because you've experienced it your entire life. You open a drawer and find it empty. You look into a container and see nothing inside. Emptiness is the absence of stuff. It's what's left when you take everything away. This seems like one of the simplest concepts in the world, so simple that it barely deserves discussion. But here's the problem. When physicists tried to create true emptiness, when they tried to make a region of space with absolutely nothing in it, they discovered something unsettling. They couldn't do it. No matter how thoroughly they removed every atom, every molecule, every particle of matter and radiation from a region, something always remained. And what remained wasn't just a technicality or an experimental limitation. It was something fundamental, something built into the structure of reality itself. To understand why empty space isn't truly empty, we need to start at the beginning. We need to understand how humanity's concept of emptiness evolved over centuries, and why every attempt to achieve perfect emptiness revealed new layers of physics hiding beneath the surface. For most of human history, the idea of a true void, a region of space containing absolutely nothing, was controversial. The ancient Greeks argued about it intensely. Aristotle, one of the most influential thinkers in Western history, declared that nature abhors a vacuum. He argued that a void was logically impossible. If you had a truly empty region of space with nothing in it, there would be no reason for anything placed in that void to move in any particular direction. There would be no resistance to motion, which meant objects would move at infinite speed, which Aristotle considered absurd. Therefore, he concluded, a vacuum cannot exist. Space must always be filled with something. Aristotle's argument wasn't silly. It was based on careful reasoning about motion and causality, and it dominated Western thought for nearly 2,000 years. Scholars, philosophers, and early scientists accepted that empty space was impossible. The universe was a plenum, a fullness. Every region of space contained matter of some kind, whether it was air, water, earth, or the mysterious fifth element, the ether, which was believed to fill the heavens. But in the 1600s, things changed. Italian physicist Evangelista Torricelli, a student of Galileo, performed an experiment in 1643 that challenged Aristotle's view directly. Torricelli filled a long glass tube, sealed at one end, with mercury. He then inverted the tube into a dish of mercury, with the open end submerged. The mercury in the tube dropped to a height of about 30 inches, leaving a space at the top of the tube above the mercury column. This space appeared to contain nothing. No air, no liquid, no visible substance. It was, as far as Torricelli could tell, empty. This was the first artificial vacuum ever created, and it caused a philosophical earthquake. If Aristotle was right that nature abhors a vacuum, how could this space exist? What was in it? Torricelli argued that the mercury column was held up by the weight of the atmosphere, pressing down on the mercury in the dish. The space above the mercury was genuinely empty, a void. He had created what we now call a Torricellian vacuum. Not everyone was convinced. Many scholars argued that the space above the Mercury wasn't truly empty. Perhaps it was filled with some invisible vapour, some subtle substance too fine to detect. The debate raged for decades. Blaise Pascal, the French mathematician and physicist, took Torricelli's experiment further in 1648. He had his brother-in-law carry a mercury barometer up a mountain, the Puy de Dôme in central France, and measure the height of the mercury at different altitudes. As they climbed higher, the mercury column dropped. At the summit, it was noticeably shorter than at the base. This proved that the atmosphere had weight and that the atmosphere's pressure was what supported the mercury column. At higher altitudes, there was less atmosphere above, so less pressure, so a shorter column. The space above the Mercury was indeed a vacuum, at least as far as air was concerned. Around the same time, Otto von Guericke, a German physicist and politician, built the first effective air pump in the 1650s. He used it for one of the most dramatic scientific demonstrations in history. He constructed two large copper hemispheres, each about 20 inches in diameter, and fitted them together to form a hollow sphere. Then he pumped the air out, creating a vacuum inside. The atmospheric pressure on the outside held the hemispheres together with tremendous force. Von Guericke hitched teams of horses to each hemisphere and had them pull in opposite directions. The horses couldn't pull the hemispheres apart. Only when air was allowed back in, equalizing the pressure, could they be separated. These were the famous Magdeburg hemispheres, and they demonstrated both the power of atmospheric pressure and the reality of the vacuum in a way no one could ignore. By the late 1600s, the existence of at least a partial vacuum was accepted. Robert Boyle in England refined the air pump and conducted extensive experiments on the properties of vacuum. He showed that sound doesn't travel through a vacuum by placing a ticking watch inside a glass jar and pumping out the air. As the air was removed, the ticking grew fainter until it became inaudible. Light, however, passed through the vacuum just fine. You could see the watch, you just couldn't hear it. This was an important clue. Sound needs a medium to travel through. It's a vibration of matter, a compression wave in air or another substance. Remove the matter and you remove the sound. But light doesn't seem to need a medium. It travels through the vacuum with no difficulty at all. Or does it? This question haunted physics for the next 2 centuries, because even though Torricelli and Boyle and von Guericke had removed the air from their chambers, even though they had created spaces with no detectable matter in them, a deep question remained. Was there truly nothing in those spaces? Or was there something else, something invisible, something undetectable by the instruments of the time, filling what appeared to be empty space? This is where the concept of a field enters the story, and it changes everything. In the early 1800s, Michael Faraday, one of the greatest experimental physicists who ever lived, began studying electricity and magnetism. Faraday was largely self-taught. He had almost no formal mathematical training, but he had extraordinary physical intuition and an ability to visualize invisible processes that few scientists have ever matched. Faraday was troubled by the idea of action at a distance. When you hold a magnet near a piece of iron, the iron is attracted to the magnet, even though they're not touching. Something reaches across the empty space between them and pulls the iron toward the magnet. What is that something? Newton had faced the same question with gravity. The sun pulls on Earth across 93 million miles of apparently empty space. How? Newton himself admitted he didn't know. He called it action at a distance and acknowledged it was deeply unsatisfying. He could describe the force mathematically with exquisite precision, but he couldn't explain how it worked. How could one object exert a force on another object that it wasn't in contact with? What carried the influence across the void? Faraday proposed a radical answer. The space between the magnet and the iron isn't empty. It's filled with something. Faraday called it a field. The magnet creates a magnetic field that extends outward in all directions, filling the space around it. The field is real. It has properties. It has a strength and a direction at every point. When you place iron filings near a magnet, and they arrange themselves in curved lines radiating from pole to pole, you're seeing the magnetic field made visible. The filings align themselves along the field lines, revealing the invisible structure that permeates the space around the magnet. This was a profound conceptual shift. Before Faraday, physicists thought of forces as acting directly between objects. Object A pulls on object B across empty space. After Faraday, physicists began thinking of forces as mediated by fields. Object A creates a field that fills the surrounding space, and object B interacts with the field at its location. The field is the intermediary. The force isn't transmitted across empty space. It's transmitted through the field that fills space. Faraday applied this thinking to electric charges as well. An electric charge creates an electric field that extends in all directions. Another charge placed in that field experiences a force, not because the first charge is reaching across space to push or pull it, but because it's responding to the field at its own location. The field is everywhere. It fills all of space, and it's always there, whether or not there's another charge present to feel it. This might seem like a subtle distinction, a philosophical preference rather than a physical difference, but it turned out to be one of the most important ideas in the history of physics. Because James Clerk Maxwell, the Scottish physicist who formalised Faraday's ideas mathematically in the 1860s, showed that fields aren't just a convenient way to think about forces, they're physical entities with their own dynamics. Fields carry energy, fields carry momentum, fields can exist independently of the charges and currents that create them. Maxwell's equations, published in their final form in 1865, unified electricity and magnetism into a single framework called electromagnetism. The equations showed that changing electric fields create magnetic fields, and changing magnetic fields create electric fields. This mutual creation allows electromagnetic disturbances to propagate through space as waves, self-sustaining oscillations of electric and magnetic fields feeding each other as they travel outward. Maxwell calculated the speed of these electromagnetic waves from the known constants of electricity and magnetism. The answer came out to approximately 300,000 kilometers per second. This was precisely the measured speed of light. Maxwell realized that light itself is an electromagnetic wave. Visible light, radio waves, infrared, ultraviolet, X-rays, gamma rays, all of these are electromagnetic waves, differing only in wavelength and frequency. This discovery had a stunning implication for the concept of emptiness. When light travels from a distant star to your eye, it crosses what appears to be empty space. Trillions of miles of apparent void. But the light is an electromagnetic wave, an oscillation of electric and magnetic fields. Those fields must exist in the space the light travels through. The light doesn't carry the fields with it like a surfer carrying a wave. The fields are already there. The light is a disturbance propagating through fields that fill all of space. Think about that carefully. When you look at a star in the night sky, the light you see has travelled for years or centuries across what appears to be the most perfect vacuum imaginable. The space between stars contains fewer than a handful of atoms per cubic centimetre. By any normal standard, it's empty. But the electromagnetic field fills that space completely. It's at every point, ready to carry electromagnetic waves, ready to transmit the light from distant stars to your eyes. The vacuum of interstellar space is full of the electromagnetic field. And it's not just the electromagnetic field. Gravity also acts across apparently empty space. The Sun's gravitational influence extends throughout the solar system and beyond, reaching across billions of miles to hold distant comets in loose orbits. In Newton's framework, this was mysterious action at a distance, but Einstein's general theory of relativity, published in 1915, provided a field-based explanation. Mass and energy create a gravitational field, which Einstein described as the curvature of space-time itself. The Sun curves the space-time around it, and the planets follow the contours of that curved space-time. The gravitational field isn't something separate from space. In Einstein's picture, the gravitational field is space, or more precisely, it's the geometric structure of space-time. So by the early 20th century, physicists had recognized at least two fundamental fields that fill all of space: the electromagnetic field and the gravitational field. These fields exist everywhere. They permeate every region of space, whether that region contains matter or not. The space between Earth and the Moon is filled with both the electromagnetic field and the gravitational field. The space between galaxies, across millions of light years of apparent void, is filled with both fields. You cannot remove these fields from space. They are intrinsic to space. They are part of what space is. This already challenges our everyday notion of emptiness. When you pump all the air out of a glass chamber, you've removed the matter. But you haven't removed the electromagnetic field. You haven't removed the gravitational field. These fields are still there, filling every point inside the chamber, ready to transmit forces and carry waves. The chamber isn't truly empty. It's full of invisible fields. But in the early 1900s, most physicists still considered these fields to be classical entities, smooth and continuous, like a calm ocean surface stretching to infinity. A classical field has a definite value at every point. You can measure the electric field strength at any location and get a precise number. The field can be zero somewhere, meaning no electromagnetic influence at that point. In a region far from any charges or magnets, with no electromagnetic waves passing through, the electromagnetic field is zero everywhere in that region. Classical physics allows this. A classical field can be exactly zero, perfectly calm, with no fluctuations and no energy. And this is where the classical picture falls apart. Because in the 1920s, physicists developed quantum mechanics, a new framework for understanding nature at its smallest scales. Quantum mechanics revealed that the smooth, continuous, perfectly calm fields of classical physics were an approximation. A very good approximation at large scales, but an approximation nonetheless. At the fundamental level, fields behave differently. They are quantum fields, and quantum fields cannot be perfectly zero. They cannot be perfectly still. They must fluctuate. To understand why, we need to briefly revisit the story of how quantum mechanics was born. In 1900, German physicist Max Planck was studying a problem called the ultraviolet catastrophe. Classical physics predicted that a hot object should radiate infinite energy at high frequencies. This was obviously wrong. Hot objects glow, but they don't emit infinite energy. Planck found that if he assumed energy comes in discrete packets, tiny indivisible units he called quanta, the mathematics gave the correct answer. Each quantum had an energy proportional to its frequency, with a proportionality constant that Planck denoted h. This constant, Planck's constant, is incredibly small, about 6.63 times 10 to the negative 34 joule seconds. Its smallness is why quantum effects are invisible in everyday life. But at atomic and subatomic scales, its effects dominate. In 1905, Albert Einstein took Planck's idea further. He proposed that light itself comes in quanta, which we now call photons. Each photon carries a specific amount of energy determined by its frequency. This explained the photoelectric effect, the observation that light shining on a metal surface ejects electrons, but only if the light's frequency is high enough. Classical wave theory couldn't explain this. Einstein's photon theory could. Light wasn't just a wave, it was also a stream of particles. This wave-particle duality became one of quantum mechanics' central features. In the 1920s, Werner Heisenberg, Erwin Schrödinger, Max Born, Paul Dirac, and others developed quantum mechanics into a full mathematical framework, and one of its most important principles was the Heisenberg uncertainty principle, formulated in 1927. This principle states that certain pairs of physical properties cannot both be precisely known simultaneously. The most famous pair is position and momentum. The more precisely you know where a particle is, the less precisely you can know how fast it's moving, and vice versa. But the uncertainty principle applies to other pairs of properties as well, and one particularly important pair is energy and time. The uncertainty in a system's energy multiplied by the uncertainty in the time over which that energy is measured must be greater than or equal to a value related to Planck's constant. The shorter the time interval, the larger the possible energy fluctuation. This has a profound consequence for fields. Consider a region of space where the electromagnetic field is supposed to be zero. In classical physics, this is straightforward. The field is zero, end of story. But in quantum mechanics, a field with a value of exactly zero at a specific time would mean you know its value with perfect precision. The uncertainty principle doesn't allow this. If you know the field's value precisely, you can't know its rate of change, and vice versa. The field must have some irreducible fuzziness, some minimum level of fluctuation that can never be eliminated, no matter what you do. These fluctuations are not caused by thermal energy or measurement disturbance or any external influence. They are intrinsic to the quantum nature of the field itself. They exist because the laws of quantum mechanics demand them. Even at absolute zero temperature, where all thermal motion has ceased and a system has the lowest possible energy, quantum fluctuations persist. This lowest energy state is called the ground state or the vacuum state, and its energy is not zero. There is always a residual energy, the zero-point energy, that can never be removed. This was the first major hint that what physicists call empty space, the vacuum, is not empty in the way we normally understand that word. The vacuum is not nothing. It is the lowest energy state of the quantum fields that fill all of space. And that lowest energy state is not zero energy. It's a seething, fluctuating, dynamic state where fields are constantly jittering at every point, everywhere, all the time. But we're getting ahead of ourselves. Before we can fully appreciate what the quantum vacuum is, we need to understand what a quantum field actually is. Not just the idea that fields exist in space, which classical physics already told us, but the specifically quantum mechanical picture that transformed our understanding of matter, energy, and reality. Because when physicists applied quantum mechanics to fields, what emerged was something no one expected. They discovered that every particle in the universe, every electron, every photon, every quark, is not a tiny independent object existing on its own. Every particle is a ripple, an excitation, a vibration in an underlying quantum field that spans the entire universe. This insight didn't come all at once. It was built over decades through the work of many physicists struggling to reconcile quantum mechanics with Einstein's special theory of relativity. The story of how quantum field theory was constructed is one of the great intellectual achievements of the 20th century, and it begins with a British physicist named Paul Dirac, who, in 1928, wrote down an equation that would change our understanding of what matter really is. But before we get to Dirac and the birth of quantum field theory, let's pause and take stock of where we are. We started with the simple idea of emptiness, an empty room, an empty glass. We traced how physicists discovered that even when you remove all matter from a region of space, fields remain. The electromagnetic field, the gravitational field, these classical fields fill all of space, making the vacuum less empty than it first appears. Then quantum mechanics entered the picture and revealed that these fields cannot be perfectly calm. They must fluctuate, even in their lowest energy state. The vacuum isn't still, it hums with quantum activity. But we've only scratched the surface, because the real revolution wasn't just discovering that classical fields have quantum fluctuations. The real revolution was discovering that fields are the fundamental things, that everything we call matter, every particle, every atom, every molecule, is made from fields, that the universe isn't made of particles moving through fields. The universe is made of fields, period. And what we call particles are just what fields do when they vibrate in certain ways. That is the story we're about to tell. To understand what a quantum field really is, we need to start with one of the deepest questions in physics. What is matter made of? You might think we answered this question a long time ago. Matter is made of atoms. Atoms are made of protons, neutrons, and electrons. Protons and neutrons are made of quarks. This is what you learn in school, and it's correct as far as it goes, but it doesn't go far enough. Because the next question is the one that changes everything. What are electrons and quarks made of? What are they really? Are they tiny little balls? Miniature spheres of stuff rattling around inside atoms? For a long time, that's roughly how physicists pictured them. Particles were imagined as little points or tiny spheres, fundamental objects that existed on their own, independent entities, moving through space, bouncing off each other, combining to form atoms and molecules and everything else in the physical world. This picture is intuitive, it's easy to visualize, and it served physics reasonably well for decades. But it's wrong. The correct picture, the one that emerged from decades of theoretical struggle and experimental confirmation, is radically different. Electrons are not tiny independent objects. Quarks are not little balls. Photons are not miniature pellets of light zipping through space. Every single one of these particles is something else entirely. Every particle is a ripple in an underlying quantum field. Let me explain what that means. Think about the surface of a calm lake. The water stretches out flat and smooth in every direction. Now imagine dropping a stone into the lake. A ripple spreads outward from the point of impact. That ripple is not a separate thing from the water. It is the water. More precisely, it's a particular behavior of the water. It's what the water does when energy is added to it in a certain way. The ripple has a location. It moves. It carries energy. You could even track it and measure its properties. But if you asked what the ripple is made of, the answer would be water. The ripple is an excitation of the water surface. It's the water surface doing something. Quantum fields work similarly, but in a much deeper and more fundamental way. Imagine that instead of a lake's surface, there is a field, an invisible entity that fills all of space. Every point, every corner, every region between the stars and within the atoms. This field is always there. It doesn't need particles to exist. It exists on its own, spread across the entire universe. Now, when this field gets excited, when energy is added to it in the right way, a localized disturbance appears. That disturbance is what we call a particle. An electron is a ripple in the electron field. A photon is a ripple in the electromagnetic field. A quark is a ripple in the quark field. Each type of particle corresponds to its own specific field. The electron field fills all of space. The quark field fills all of space. The electromagnetic field fills all of space. All these fields coexist, overlapping, occupying the same regions simultaneously, each one ready to produce its corresponding particle whenever it receives the right amount of energy in the right configuration. This means particles are not fundamental. Fields are fundamental. Particles are what fields do. They are behaviors of fields, patterns of excitation, temporary concentrations of energy in an underlying medium that spans the cosmos. This is the central insight of quantum field theory, and it is one of the most important ideas in the history of science. But how did physicists arrive at this picture? It didn't happen overnight. It took decades of work, starting with a crisis that emerged almost as soon as quantum mechanics was born. In the mid-1920s, quantum mechanics was brand new. Heisenberg, Schrödinger, Born, and others had developed a mathematical framework that could describe the behavior of particles at atomic scales with astonishing accuracy. Schrödinger's equation, formulated in 1926, told you how the quantum state of a particle evolves over time. You could use it to calculate the energy levels of hydrogen, the behavior of electrons in atoms, the probabilities of different measurement outcomes. It worked beautifully. But there was a problem. Schrödinger's equation was not consistent with Einstein's special theory of relativity. Special relativity, published in 1905, showed that space and time are intertwined. The laws of physics must look the same to all observers moving at constant velocity relative to each other. Energy and momentum are related in a specific way that involves the speed of light. Mass and energy are equivalent through the famous equation E equals mc squared. Schrödinger's equation didn't respect these relationships. It treated time and space differently, giving time a special role that relativity doesn't allow. It worked well for slow-moving particles, much slower than the speed of light, but it couldn't handle particles moving at relativistic speeds, and it certainly couldn't handle photons, which always travel at the speed of light. This was a serious issue. If quantum mechanics was supposed to be a fundamental theory of nature, it had to be compatible with relativity. Nature doesn't give you a choice between the two. Both quantum mechanics and relativity are true. Any complete theory must incorporate both. In 1928, Paul Dirac, a young British physicist working at Cambridge, took on this challenge. Dirac was one of the most brilliant theoretical physicists of the 20th century. He was quiet, precise, and almost pathologically logical. He once said that the laws of physics should have mathematical beauty, and he pursued that beauty with single-minded intensity. Dirac set out to write a quantum equation for the electron that was fully compatible with special relativity. The result was the Dirac equation, and it was a masterpiece. It described the electron perfectly at relativistic speeds. It naturally predicted the electron's spin, a quantum property that had been observed experimentally, but had seemed mysterious and arbitrary in Schrödinger's framework. In Dirac's equation, spin wasn't added by hand. It emerged automatically from the mathematics of combining quantum mechanics with relativity. This was a powerful sign that Dirac was on the right track. But the Dirac equation also predicted something no one expected. It had solutions with negative energy. In Schrödinger's equation, electrons could have positive energy, kinetic energy, and potential energy in familiar combinations. But Dirac's equation allowed electrons to have negative energy as well. This was deeply puzzling. If negative energy states existed, why didn't all electrons fall into them? In physics, systems tend to seek their lowest energy state. If negative energy states were available, electrons should cascade down into them, releasing energy as they fell. Atoms would be unstable. Matter would collapse. The universe as we know it couldn't exist. Dirac proposed a bold solution. He suggested that all the negative energy states are already filled. Every single negative energy state is occupied by an electron. You can't see these electrons because they fill every point in space uniformly, forming a kind of invisible sea. Dirac called this the Dirac sea. Because the negative energy states are all occupied, the Pauli exclusion principle, which says two electrons cannot occupy the same quantum state, prevents ordinary electrons from falling into them. The sea is full. There's no room for more electrons. But here's where it gets remarkable. Dirac realized that if you added enough energy to one of the electrons in this sea, you could kick it out of its negative energy state and into a positive energy state. The electron would appear as a normal, observable electron, but it would leave behind a hole in the sea. That hole, the absence of a negative energy electron, would behave exactly like a particle with positive energy and positive charge. It would look like an electron with the opposite charge. Dirac had predicted the existence of a particle that no one had ever seen, the positron, the antimatter partner of the electron. In 1932, American physicist Carl Anderson discovered the positron in cosmic ray experiments. He observed a particle with the same mass as an electron, but with positive charge, exactly as Dirac had predicted. It was one of the most stunning confirmations of a theoretical prediction in the history of science. Dirac had derived the existence of antimatter purely from the mathematics of combining quantum mechanics with relativity. But the Dirac C picture, while it made correct predictions, was also deeply uncomfortable. It required an infinite number of invisible electrons filling all of space. Every point in the universe was saturated with negative energy electrons you couldn't see. This didn't feel right. It seemed like an awkward mathematical trick rather than a genuine description of reality. And it didn't generalize well to other particles. The Dirac C worked for electrons because electrons obey the Pauli exclusion principle. But photons don't. They're bosons, particles that can occupy the same quantum state in unlimited numbers. You can't fill a sea of photon states because there's no exclusion principle to make the sea stable. The resolution came through quantum field theory. Instead of thinking about individual particles, with or without a sea of negative energy particles filling space, physicists learned to think about fields. The electron field fills all of space. When it's in its lowest energy state, its ground state, no electrons are present. The field is calm, quiet, fluctuating gently but not excited enough to produce particles. When the field is excited, a ripple appears. That ripple is an electron. When the field is excited in a different way, another ripple appears. That ripple is a positron. Both particles emerge from the same underlying field. The electron and the positron are not fundamentally different things. They are different modes of excitation of the same field, like different notes played on the same instrument. This was a far cleaner and more elegant picture than the Dirac C. It eliminated the need for an infinite number of invisible particles filling space. Instead, there's just a field. When the field is quiet, you see no particles. When it's excited, you see electrons or positrons, depending on the type of excitation. The field is the fundamental entity. Particles come and go as the field gains and loses energy. The development of this picture was not the work of one person. It was a collective achievement spanning the 1930s, 40s, and 50s, involving many of the greatest physicists of the 20th century. In the late 1920s and early 1930s, Dirac himself, along with Wolfgang Pauli, Werner Heisenberg, Pascual Jordan, and others, began constructing the mathematical framework for quantum field theory. Jordan was particularly important. He showed how to treat the electromagnetic field quantum mechanically, describing photons as quantized excitations of the field. This was quantum electrodynamics in its earliest form, the quantum theory of how light and matter interact. But the early attempts at quantum field theory ran into severe problems. When physicists tried to calculate the properties of electrons and photons using the new framework, they kept getting infinities. The calculations blew up. The probability of an electron scattering off another electron, for example, came out as infinity rather than a finite number. The self-energy of the electron, the energy associated with the electron's own electromagnetic field, came out as infinity. Everywhere they looked, infinities appeared. The mathematics seemed to be telling them that the theory was broken. This was called the problem of infinities, and it paralyzed quantum field theory for nearly 2 decades. Many physicists despaired. Some thought the approach was fundamentally wrong and that a completely different framework was needed. Even Dirac became pessimistic about quantum field theory's future. The infinities seemed to indicate a deep sickness in the theory that couldn't be cured. The breakthrough came in the late 1940s. 3 physicists, working largely independently, Richard Feynman, Julian Schwinger, and Shinichiro Tominaga, each found ways to handle the infinities. Their approaches were mathematically different, but physically equivalent, as Freeman Dyson later proved. The technique they developed is called renormalization. The basic idea is subtle but powerful. The infinities arise because the theory, in its raw form, describes electrons interacting with their own electromagnetic fields at arbitrarily short distances. At very tiny distances, the interactions become infinitely strong. But you never actually measure the raw, bare properties of an electron. What you measure are the effective properties. the charge and mass of the electron as seen from a distance, dressed in its cloud of virtual particles and field interactions. Renormalization systematically separates the infinite raw quantities from the finite measured quantities, absorbing the infinities into the definitions of the electron's observed mass and charge. What remains after renormalization are finite, calculable predictions that can be compared with experiment, and the agreement with experiment was breathtaking. Quantum electrodynamics, or QED as it came to be known, became the most precisely tested theory in all of science. Its predictions match experimental measurements to better than 10 decimal places. The magnetic moment of the electron, for instance, has been calculated using QED and measured independently, and the two numbers agree to better than 1 part in a trillion. This is like measuring the distance from New York to Los Angeles and being accurate to within the width of a human hair. No other theory in any branch of science has ever achieved this level of agreement between prediction and measurement. Feynman developed a particularly intuitive way to visualize quantum field theory calculations. He invented diagrams, now called Feynman diagrams, that represent particle interactions as simple pictures. An electron is drawn as a straight line. A photon is drawn as a wavy line. When an electron emits or absorbs a photon, the lines meet at a point called a vertex. You can combine these basic elements into more and more complex diagrams representing different physical processes. Each diagram corresponds to a specific mathematical expression. To calculate the probability of a process, you draw all possible diagrams and add up their contributions. These diagrams look simple, almost childlike, but they encode the full power of quantum field theory. They make it possible to systematically calculate the probabilities of particle interactions to any desired precision by including more and more complex diagrams. The simplest diagrams give the dominant contribution. More complex diagrams give smaller corrections. The more diagrams you include, the more precise your calculation becomes. But Feynman diagrams also reveal something profound about the nature of reality. In these diagrams, particles are constantly being created and destroyed. An electron traveling through space doesn't just travel peacefully from one point to another. According to quantum field theory, it continuously emits and reabsorbs virtual photons. These virtual photons are brief excitations of the electromagnetic field that exist for incredibly short times before being reabsorbed. The electron is surrounded by a cloud of these virtual photons, a haze of electromagnetic field activity that accompanies it everywhere. And it goes further. Those virtual photons can themselves briefly create virtual electron-positron pairs, little ripples in the electron field that pop into existence and vanish almost instantly. These pairs create their own virtual photons, which create more pairs, and so on. The simple picture of a single electron moving through empty space becomes an incredibly complex web of field excitations, a constant bubbling of activity in the quantum field surrounding the electron. This isn't just theoretical abstraction. These virtual processes have measurable effects. The cloud of virtual particles around an electron slightly modifies its magnetic properties, its interaction with other particles, and its effective mass. These modifications, calculated through Feynman diagrams and renormalization, match experimental measurements with extraordinary precision. The virtual particles are not real in the same sense that a detected particle is real. You can't capture a virtual photon in a detector, but their effects on measurable quantities are undeniable. The success of QED inspired physicists to apply the same quantum field theory framework to other forces. In the 1960s and 70s, the weak nuclear force, responsible for certain types of radioactive decay, was unified with electromagnetism into the electroweak theory by Sheldon Glashow, Abdus Salam, and Steven Weinberg. This theory introduced new quantum fields, the W and Z fields, whose excitations are the W and Z bosons. These particles were predicted theoretically and then discovered experimentally at CERN in 1983, another triumph of quantum field theory. The strong nuclear force, which holds quarks together inside protons and neutrons, was described by quantum chromodynamics, or QCD. This theory introduces quark fields and gluon fields. Quarks carry a property called color charge, analogous to electric charge, but coming in 3 types instead of 1. Gluons are the excitations of the gluon field. They carry the strong force between quarks, binding them tightly inside protons and neutrons. Unlike photons, which don't carry electric charge and therefore don't interact directly with each other, gluons carry color charge and do interact with each other. This makes the strong force behave very differently from electromagnetism. It gets stronger at larger distances rather than weaker, which is why quarks are permanently confined inside protons and neutrons. You can never isolate a single quark. If you try to pull one away, the energy you invest creates new quarks, producing new bound states rather than freeing the original quark. Together, quantum electrodynamics, the electroweak theory, and quantum chromodynamics form the standard model of particle physics. The standard model is the most comprehensive and precisely tested theory of fundamental physics ever constructed. It describes 3 of the 4 known fundamental forces: electromagnetism, the weak force, and the strong force. And it catalogues all known fundamental particles. And here's the key point. In the standard model, every particle is an excitation of a quantum field. There are 12 matter fields whose excitations are the fundamental fermions, 6 quark fields, 1 for each flavour of quark: up, down, charm, strange, top and bottom. 3 charged lepton fields for the electron, the muon and the tau. And 3 neutrino fields for the electron neutrino, the muon neutrino and the tau neutrino. There are gauge boson fields whose excitations carry the forces, the electromagnetic field whose excitations are photons, the weak fields whose excitations are the W+, W- and Z bosons, and the gluon fields whose excitations are the 8 types of gluons. And there is the Higgs field whose excitation is the Higgs boson, discovered at CERN in 2012. Each of these fields fills all of space. Every point in the universe right now, at this very moment, is simultaneously occupied by the electron field, the up quark field, the down quark field, the electromagnetic field, the gluon fields, the Higgs field, and all the others. These fields overlap, coexist, and interact with each other at every location. They're not separate layers stacked on top of each other. They're all present simultaneously, filling the same 3-dimensional space. When physicists say there are roughly 17 fundamental quantum fields in the standard model, they mean that the entire physical world, everything you see, everything you touch, every star, every planet, every living cell, every thought in your brain, is ultimately made from excitations of these fields. You are not made of particles in the old-fashioned sense of tiny independent objects. You are made of field excitations. You are a complex, intricately organized pattern of ripples in quantum fields. This is worth dwelling on. Your hand is made of atoms. Those atoms are made of electrons, protons, and neutrons. The electrons are excitations of the electron field. The protons and neutrons are made of quarks, which are excitations of quark fields, bound together by gluons, which are excitations of gluon fields. The quarks and electrons interact by exchanging photons, which are excitations of the electromagnetic field. Every component of your hand, at the deepest level, is a pattern of vibration in a quantum field. And those fields are not contained within your hand, they extend far beyond it. The electron field in your hand is the same electron field that fills the space between you and the nearest star. It's the same electron field that exists at the edge of the observable universe. There is only one electron field. It is everywhere. When an electron exists in your hand, and another electron exists in a laboratory in Geneva, both of them are excitations of the same single field. They're like two ripples on the same ocean, separated by distance, but fundamentally part of the same thing. This is why all electrons are identical. Every electron in the universe has exactly the same mass, exactly the same charge, exactly the same spin, exactly the same magnetic moment. Not approximately the same, exactly the same. In the old particle picture, this was mysterious. If electrons were independent little objects, why would they all have precisely the same properties? You'd expect some variation, some manufacturing tolerance. When you make billions of anything, whether it's ball bearings or grains of sand, they're all slightly different. But electrons are identical to arbitrary precision. Why? Quantum field theory explains this naturally. All electrons are identical because they're all excitations of the same field. They're all the same kind of ripple in the same underlying entity. Just as all waves on the same ocean are made of water, all electrons are made of the electron field. Their properties aren't determined by individual manufacturing, but by the properties of the field itself. The electron field has certain characteristics: its mass parameter, its charge coupling, its spin structure, and every excitation of that field inherits those same characteristics. Identical fields produce identical particles. It couldn't be any other way. This also explains why particles can be created and destroyed. In the old picture, particles were permanent objects. You could move them around, combine them, separate them, but the total number of particles was supposed to stay the same. Conservation of matter, as chemists call it. But in reality, particles are created and destroyed all the time. When a gamma-ray photon with enough energy passes near a nucleus, it can transform into an electron and a positron. One particle becomes two. The photon vanishes and two new particles appear. In the old particle picture, this is baffling. How does a particle of light turn into two particles of matter? Where does the matter come from? In the field picture, it's natural. The photon is an excitation of the electromagnetic field. As it interacts with the electron field, it transfers its energy to that field. The electron field uses that energy to create two new excitations, an electron and a positron. The electromagnetic field calms down at that point, and the electron field gets excited. Energy moved from one field to another. No mysterious creation of matter from nothing. Just energy being transferred between fields, changing which fields are excited and which are calm. Similarly, when an electron and a positron collide, they annihilate each other, producing two or more photons. In the field picture, the excitations in the electron field cancel out, releasing their energy back into the electromagnetic field, which uses it to produce photon excitations. Again, just energy moving between fields. This picture also clarifies what antimatter really is. A positron is not some exotic opposite of an electron from a mirror universe. It's simply the electron field excited in a different mode. The electron field supports two types of excitation. One we call the electron, and the other we call the positron. They have the same mass, but opposite charge. When they meet, the two excitations cancel each other out, returning the field to a calmer state and releasing the energy as photons. The concept of a quantum field also helps explain forces between particles. In classical physics, forces act between objects across empty space. Two electrons repel each other. Why? In the quantum field picture, the force between electrons is mediated by the electromagnetic field. One electron disturbs the electromagnetic field around it, creating a disturbance that propagates outward. The other electron feels this disturbance and responds. At the quantum level, this process is described by the exchange of virtual photons. The two electrons exchange virtual photons back and forth, and the momentum carried by these virtual photons is what we experience as the electromagnetic force. The word virtual here is important. Virtual photons aren't photons you can catch with a detector. They're intermediate excitations of the electromagnetic field that exist only during the interaction process. They're allowed by the uncertainty principle to exist briefly, borrowing energy for a short time. Their existence is fleeting and indirect, but their effects are real. Every force you experience, the rigidity of the chair you're sitting in, the friction of your shoes on the floor, the light entering your eyes, all of these are ultimately the result of quantum fields exchanging virtual particles. Let me make sure the central point is absolutely clear, because it cannot be overstated. In modern physics, particles are not the fundamental building blocks of nature. Fields are. Particles are secondary. They are derived. They are what you get when a field is excited above its ground state. If the field is calm, there are no particles. If the field is disturbed, particles appear. The field exists regardless. It's always there, at every point in space, whether or not any particles are present. The field is the reality. The particle is the phenomenon. This is not a metaphor. It's not a teaching tool or a simplification. It is the actual content of our best physical theories. The standard model of particle physics, tested to extraordinary precision over decades, is a quantum field theory. It describes nature in terms of fields, their excitations, and their interactions. Every prediction it makes, and it has made thousands of confirmed predictions, is calculated using the mathematics of quantum fields. When CERN discovered the Higgs boson in 2012, what they actually detected was evidence that the Higgs field exists and can be excited. The boson was the excitation. The field was the fundamental reality they were confirming. And this brings us to the most remarkable implication of all. These fields don't go away when there are no particles. The electron field doesn't vanish when there are no electrons around. The quark field doesn't disappear when no quarks are present. The electromagnetic field doesn't cease to exist in a region with no photons. The fields are always there. Every quantum field in the standard model fills all of space at all times. In a region where no particles are present, where no matter exists, where by any ordinary definition the space is empty, all of these fields are still present. They're in their ground state, their lowest energy configuration, but they're there. They haven't gone anywhere. They can't go anywhere. They are part of the fabric of reality. This means that what we casually call empty space, the vacuum, the void between stars, the gap between atoms, is not empty at all. It is filled with quantum fields, all of them, overlapping, coexisting, quietly fluctuating in their ground states, ready to produce particles the instant enough energy is available. Empty space is not nothing. It is a state of something. It is the quietest possible state of an incredibly rich, complex, multi-layered system of quantum fields. And even in that quietest state, the fields are not perfectly still. They can't be. The Heisenberg uncertainty principle forbids it. What does it mean for these fields to fluctuate in the vacuum? What are the physical consequences? Can we actually detect the effects of quantum field fluctuations in supposedly empty space? The answer, as we're about to discover, is yes. The quantum vacuum is not a theoretical curiosity. It has real, measurable, experimentally confirmed physical effects. And those effects prove beyond any doubt that empty space is one of the most interesting and active places in the entire universe. We've established something extraordinary. Every point in the universe is filled with quantum fields. Not one field, but many. The electron field, the quark fields, the electromagnetic field, the gluon fields, the Higgs field, and others. These fields are always present, always filling space, whether or not any particles exist. Particles are just excitations of these fields, temporary ripples in an underlying reality that persists even when no ripples are visible. But now we need to confront a question that takes us even deeper. If these fields fill all of space, what are they doing when no particles are present? What is the state of the fields in supposedly empty space? What is the vacuum really? In everyday language, vacuum means nothing, an empty container, a void, the absence of everything. But in quantum field theory, the vacuum has a precise technical meaning that is profoundly different from everyday emptiness. The vacuum is the lowest energy state of all the quantum fields. It is not the absence of everything. It is the quietest possible configuration of everything. All the fields are still there. They haven't been removed. They haven't been switched off. They are simply in their ground state, the state with the least possible energy. And here is the critical point. The least possible energy is not zero energy. This is where quantum mechanics forces us to abandon our intuitive understanding of emptiness. In classical physics, a field in its lowest energy state has zero energy everywhere. The field value is exactly zero at every point. Nothing is happening. The field is perfectly still, perfectly calm, perfectly silent. This is what classical emptiness looks like. A field at rest with no energy, no activity, no fluctuations of any kind. But quantum mechanics does not allow this. The Heisenberg uncertainty principle, one of the foundational pillars of quantum physics, forbids any quantum system from having a perfectly defined value with zero uncertainty. This applies to all quantum systems, including fields. A quantum field cannot have a value of exactly zero with zero rate of change at every point simultaneously. If the field value were exactly zero everywhere, you would know its value with perfect precision, which would mean its conjugate quantity, related to the rate of change of the field, would be completely uncertain. The field would have to be wildly fluctuating in its rate of change. Conversely, if the rate of change were exactly zero everywhere, the field value itself would be uncertain. You cannot pin down both simultaneously. This is not a limitation of our instruments or our knowledge. It is a fundamental property of quantum reality. The consequence is that quantum fields in their ground state are never perfectly still. They fluctuate, constantly, at every point in space. These fluctuations are called vacuum fluctuations, or zero-point fluctuations. They represent the irreducible minimum of quantum activity that exists, even when the universe is in its lowest possible energy state. Even if you cooled a region of space to absolute zero, removed every particle of matter and every photon of radiation, and created the most perfect vacuum physically possible, these fluctuations would persist. They are not caused by thermal motion. They are not caused by stray particles or external disturbances. They arise from the quantum nature of the fields themselves. To understand this more concretely, think about a simple quantum system, a quantum harmonic oscillator. This is the quantum version of a mass on a spring. In classical physics, you can bring the mass to rest at the equilibrium position and leave it there. It sits perfectly still with zero energy. But in quantum mechanics, the ground state of a harmonic oscillator has a non-zero energy, called the zero-point energy. The mass can never be perfectly at rest. It always has some residual jitter, some irreducible motion. You can cool it down, remove all thermal energy, bring it to its absolute lowest state, and it still vibrates. Not because something is shaking it, but because quantum mechanics demands it. A quantum field is essentially an infinite collection of coupled harmonic oscillators, one at every point in space. Each oscillator represents the field's tendency to fluctuate at that point, and each one has its own zero-point energy. The total zero-point energy of a quantum field, summed over all points in space and all possible frequencies of fluctuation, is enormous. In fact, a naive calculation gives an infinite total energy for the vacuum. This is one of the deep puzzles of quantum field theory, and we'll return to it later. But the fluctuations themselves, the jittering of the field at each point, are real. They have measurable consequences, and those consequences have been confirmed experimentally with extraordinary precision. Let me walk you through the evidence, because this isn't speculation, this isn't philosophy, this is physics backed by experiments that you could, in principle, replicate in a laboratory. The first and most famous piece of evidence is the Casimir effect. In 1948, Dutch physicist Hendrik Casimir made a remarkable prediction. He calculated that two uncharged, perfectly conducting metal plates placed very close together in a vacuum would experience a force pushing them toward each other. Not because of gravity, not because of static electricity, not because of any classical force, but because of the quantum fluctuations of the electromagnetic field in the space between them and around them. Here's how it works. The electromagnetic field fluctuates everywhere, even in the vacuum. These fluctuations occur at all possible wavelengths. Some fluctuations have very short wavelengths, others have very long wavelengths, and there's a continuous spectrum in between. In the open space outside the plates, all wavelengths of fluctuation are permitted. There are no restrictions. The field can fluctuate at any frequency it likes. But between the plates, the situation is different. The plates impose boundary conditions on the electromagnetic field. The conducting surfaces require the electric field to be zero at the plate surfaces. This means that only certain wavelengths of fluctuation can fit between the plates, those whose half wavelengths are integer multiples of the gap between the plates. It's like standing waves on a guitar string. A guitar string fixed at both ends can only vibrate at certain frequencies, the fundamental and its harmonics. Similarly, the electromagnetic field between two plates can only fluctuate at certain wavelengths, those that fit neatly between the plates with zero field at each surface. This restriction means there are fewer fluctuation modes between the plates than outside them. Outside the plates, all modes are present. Between the plates, some modes are excluded. Since each fluctuation mode carries zero-point energy, there is less vacuum energy between the plates than outside them. This energy difference creates a pressure imbalance. There is more vacuum pressure pushing on the plates from outside than from between them. The result is a net force pushing the plates together. Casimir calculated the magnitude of this force. It depends on the area of the plates and on the fourth power of the inverse of the distance between them. The closer the plates, the stronger the force. For plates separated by about 1 micrometer, roughly 1/100th the width of a human hair, the force is extremely small, but not negligibly so. It corresponds to a pressure of about 1/1000th of a pascal, tiny compared to atmospheric pressure, but well within the range of sensitive laboratory instruments. For decades after Casimir's prediction, the effect was not measured directly because the force is so tiny, and the plates must be so close together and so perfectly flat. But in 1997, physicist Steve Lamoureux at the University of Washington performed a precision experiment that confirmed the Casimir effect. He used a metal plate and a metal sphere, carefully controlling the distance between them and measuring the tiny force with sensitive instruments. His results matched Casimir's prediction to within 5%. Since then, numerous experiments have confirmed the Casimir effect with ever-increasing precision. Modern measurements agree with the theoretical prediction to better than 1%. The force is real, it's measurable, it pushes physical objects together, and its cause is nothing other than the quantum fluctuations of the electromagnetic field in the vacuum. The vacuum is not empty, it has structure, it has energy, and that energy can exert a physical force on matter. The second major piece of evidence for vacuum fluctuations comes from atomic physics. It's called the Lamb shift, and it was one of the discoveries that helped launch modern quantum electrodynamics. In 1947, American physicist Willis Lamb and his graduate student Robert Rutherford performed a precise measurement of the energy levels of hydrogen. According to Dirac's equation, two particular energy levels of the hydrogen atom, called the 2s1/2 and 2p1/2 states, should have exactly the same energy. They should be degenerate, as physicists say, but Lamb and Rutherford found that they don't. The 2s1/2 state has slightly more energy than the 2p1/2 state. The difference is tiny, corresponding to a frequency of about 1057 MHz, but it was unmistakable. Dirac's equation, for all its brilliance, was slightly wrong. What causes this discrepancy? The answer lies in vacuum fluctuations. The electron in a hydrogen atom doesn't just sit calmly in its orbit. It is constantly buffeted by the fluctuations of the electromagnetic field in the vacuum. Even though no real photons are present, the vacuum fluctuations of the electromagnetic field jostle the electron slightly, causing it to jitter around its average position. This jittering affects the electron's energy in a way that depends on its orbital shape. The 2s1/2 orbital is spherically symmetric. The electron spends some of its time very close to the nucleus, where the electric field is strongest. The 2p1/2 orbital has a different shape. The electron avoids the nucleus, never getting as close. Because the vacuum fluctuations cause the electron to sample slightly different regions of the electric field, the energy shift depends on the shape of the orbital. The 2s1/2 state, where the electron gets closer to the nucleus, experiences a different shift than the 2p1/2 state. The result is a tiny energy difference between two states that Dirac's equation predicted should be identical. Hans Bethe, a German-American physicist, calculated this shift in 1947 using the new techniques of quantum electrodynamics. His calculation, done famously on a train ride from New York, matched Lam's measurement remarkably well. Later, more precise calculations using the full machinery of renormalized QED reproduced the Lam shift to extraordinary accuracy. The agreement between theory and experiment is now better than 1 part in a million. The Lam shift is direct evidence that vacuum fluctuations affect the behavior of real particles. The jittering of the electron caused by the quantum fluctuations of the electromagnetic field in supposedly empty space produces a measurable change in the energy levels of hydrogen. The vacuum is not passive, it's active. It interacts with matter, it changes how atoms behave. There's a third piece of evidence that's even more fundamental and ubiquitous. It's called spontaneous emission, and it happens every time an atom emits light. When an atom is in an excited state, it has more energy than it does in its ground state. Classical physics has no mechanism to make the atom lose this energy on its own. In classical electrodynamics, a charged particle radiates energy only when it accelerates. An electron sitting in a stable orbit, even an excited orbit, shouldn't radiate. Something has to push it down. An external perturbation, a collision with another atom, something from outside. But in reality, atoms in excited states don't wait for an external push. They spontaneously emit a photon and drop to a lower energy state, all on their own. No collision required, no external influence needed. The atom just does it, spontaneously. This is why hot objects glow. This is why neon lights shine. This is why stars emit light. Excited atoms spontaneously release photons without any apparent cause. What triggers spontaneous emission? Vacuum fluctuations. The quantum fluctuations of the electromagnetic field in the vacuum constantly perturb the excited atom, jostling it in random ways. These perturbations are the same vacuum fluctuations that cause the Lam shift and the Casimir effect. They couple to the excited electron and stimulate it to release its excess energy as a photon, dropping to a lower state. Without vacuum fluctuations, spontaneous emission would not occur. Atoms would stay in excited states indefinitely, waiting for something external to knock them down. Light as we know it would not work the same way. The process by which the sun shines, by which fire glows, by which your eyes receive photons from the world around you, all of it ultimately depends on the fact that the vacuum is not empty. Einstein himself provided early insight into this in 1917, long before quantum field theory was fully developed. He was studying the statistics of how atoms emit and absorb radiation, and he found that to get the correct thermal equilibrium distribution of photon energies, he had to include a term for spontaneous emission, alongside the terms for stimulated emission and absorption. Stimulated emission happens when a passing photon triggers an atom to emit an identical photon. Absorption happens when a photon is consumed by an atom. But spontaneous emission couldn't be explained by these processes alone. Something else was needed. That something as later understood through quantum field theory, was the vacuum fluctuations of the electromagnetic field. They provide the perturbation that stimulates the so-called spontaneous emission. Let me mention one more piece of evidence because it's particularly beautiful. It's the anomalous magnetic moment of the electron, sometimes called the electron G-factor anomaly. This is one of the most precisely measured quantities in all of science, and its agreement with quantum field theory is arguably the single greatest triumph of theoretical physics. Every electron behaves like a tiny magnet. It has a magnetic moment related to its spin. Dirac's equation predicts that the electron's gyromagnetic ratio, called G, should be exactly 2. But experiments show that G is slightly larger than 2. The difference is tiny, about 0.0023, but it's definitely there. This anomaly arises because the electron doesn't exist in isolation. It's constantly interacting with the quantum vacuum. Virtual photons are emitted and reabsorbed. Virtual electron-positron pairs briefly appear in the electron's vicinity. All the quantum fields in the vacuum contribute tiny corrections to the electron's magnetic moment. Julian Schwinger calculated the first correction in 1948, finding that G equals 2 plus alpha divided by pi, where alpha is the fine structure constant, roughly 1 over 137. This gave a correction of about 0.00232, in beautiful agreement with experiment. Since then, physicists have calculated higher order corrections involving more and more complex virtual processes. The current theoretical prediction, which includes contributions from thousands of Feynman diagrams involving virtual photons, virtual electron-positron pairs, and even virtual muon and tau pairs, agrees with the experimental measurement to better than 12 significant figures. Let me say that again because it deserves emphasis. The theoretical prediction, which is entirely based on the electron interacting with vacuum fluctuations, with the quantum fields in supposedly empty space, matches the measured value to 12 decimal places. This is the most precise agreement between theory and experiment in the entire history of science. There is no other measurement in any field of human knowledge, not in engineering, not in chemistry, not in biology, not in any branch of physics outside quantum field theory, that comes even close to this level of precision and confirmation. And this precision depends entirely on the vacuum being active, on quantum fields fluctuating, even when no real particles are present. If you removed the vacuum fluctuation contributions from the calculation, if you pretended that empty space was truly empty, with no field activity at all, the prediction would be wrong. It wouldn't be slightly wrong, it would disagree with experiment by a measurable amount. The vacuum fluctuations are not optional, they are essential. They are part of how reality works. So let's step back and absorb what these experiments are telling us. The Casimir effect demonstrates that vacuum fluctuations create measurable forces between physical objects. The Lamb shift demonstrates that vacuum fluctuations alter the energy levels of atoms. Spontaneous emission demonstrates that vacuum fluctuations trigger real physical processes that produce the photons we see all around us. And the electron's anomalous magnetic moment demonstrates that vacuum fluctuations modify the fundamental properties of particles to 12 decimal places of precision. These are not marginal effects. They are not curiosities tucked away in footnotes. Spontaneous emission is responsible for virtually all the light you have ever seen. The Lamb shift was a pivotal discovery that drove the development of quantum electrodynamics, one of the most important theories in the history of physics. The Casimir effect is increasingly relevant to nanotechnology and the design of microelectromechanical systems, where surfaces are separated by tiny distances. And the electron G-factor is the gold standard of precision physics. All of this tells us the same thing. The vacuum is not empty. It is the ground state of quantum fields, and that ground state is physically active, measurably real, and essential to the functioning of the universe as we know it. Now, this raises a very natural question. If the vacuum has energy, if quantum fluctuations carry real physical power capable of pushing plates together and shifting atomic energy levels, how much energy does the vacuum actually contain? This is where things get deeply strange and deeply humbling. Because when physicists calculate the total energy density of the vacuum using quantum field theory, they get a number that is absurdly, incomprehensibly large. The calculation involves summing up the zero-point energy contributions from all possible fluctuation modes at all possible wavelengths down to the smallest scales where we think our theories apply. The result depends on what you choose as your cutoff, the smallest wavelength you include in the sum. If you sum all the way down to the Planck length, which is the smallest distance scale that has physical meaning, the vacuum energy density comes out to roughly 10 to the 113 joules per cubic meter. That number is so large it's almost meaningless. To put it in some kind of perspective, the energy density of a nuclear explosion is about 10 to the 15 joules per cubic meter. The vacuum energy density predicted by naive quantum field theory is roughly 10 to the 98 times larger than a nuclear explosion in every cubic meter of empty space. If this calculation were correct, the vacuum would contain more energy per cubic meter than all the matter and radiation in the observable universe combined. Every cubic centimeter of empty space would hold more energy than the total output of the Sun over its entire lifetime. Obviously, something is wrong with this calculation, or rather, something is missing from our understanding, because the universe does not behave as though the vacuum contains this much energy. If the vacuum energy were really that large, it would have catastrophic gravitational effects. Einstein's general theory of relativity tells us that energy, all energy, creates gravity. The vacuum energy would curve space-time enormously, causing the universe to expand at a mind-boggling rate, or collapse in on itself almost instantly, depending on the sign of the energy. The universe as we know it, with its galaxies and stars and planets and living things, could not exist. This discrepancy between the predicted vacuum energy and the observed behavior of the universe is called the cosmological constant problem, and it is one of the most profound unsolved puzzles in all of physics. The observed value of the vacuum energy, inferred from the accelerating expansion of the universe discovered in 1998, is not zero. The universe is expanding at an accelerating rate, which implies there is some energy associated with empty space, something physicists call dark energy. But the observed vacuum energy density is roughly 10 to the minus 9 joules per cubic meter. Compare that with the theoretical prediction of 10 to the 113 joules per cubic meter. The prediction is off by a factor of roughly 10 to the 122. That's not just a big error. It is the largest discrepancy between theory and observation in the entire history of science. It's not off by a factor of 10 or 100 or a million. It's off by a factor of 1 followed by 122 zeros. Nothing else in physics comes close to this level of disagreement. Many physicists consider this the most important unsolved problem in fundamental physics. Some think it hints at something deep we're missing about quantum field theory. Perhaps the naive calculation of vacuum energy is wrong in some fundamental way. Perhaps there's a symmetry we haven't discovered that cancels most of the vacuum energy, leaving only the tiny residual we observe. Supersymmetry, a theoretical framework that proposes a partner particle for every known particle, would cancel boson and fermion contributions to the vacuum energy. But supersymmetry, if it exists, must be broken at some energy scale because we haven't observed superpartner particles. The residual vacuum energy after supersymmetry breaking is still far too large, though much smaller than the original prediction. Others think the cosmological constant problem might be connected to quantum gravity, the as yet undiscovered theory that unifies quantum mechanics with general relativity. Our current theories might simply not apply to vacuum energy in the way we think they do. When we finally understand quantum gravity, the vacuum energy calculation might come out differently. Still others invoke the anthropic principle, The idea that the vacuum energy has the value it does, because if it were much larger, the universe would have expanded too fast for galaxies to form, and we wouldn't be here to measure it. In a multiverse with many different regions having different vacuum energies, we necessarily find ourselves in a region with a small enough vacuum energy for complexity and life to develop. None of these explanations is fully satisfactory. The cosmological constant problem remains open. It stands as a reminder that our understanding of the vacuum, while remarkably detailed and experimentally confirmed in many ways, is still fundamentally incomplete. We know the vacuum is not empty. We know it contains fluctuating quantum fields. We know those fluctuations have real physical effects. But we don't fully understand the gravitational implications of vacuum energy. Something important is missing from our picture. What we do know is this: the vacuum, the supposed emptiness of space, is one of the richest and most complex physical systems in the universe. It's not nothing. It's a state of quantum fields, and that state has energy, has structure, has measurable consequences. The old picture of empty space as a passive, featureless void in which particles move and interact has been replaced by a picture of empty space as a dynamic, active medium, humming with quantum fluctuations at every point, filled with overlapping fields that are never truly still. When you sit in a quiet room and listen to the silence, you are surrounded by quantum fields in their ground state. The electromagnetic field fluctuates around you. The electron field fluctuates through you. The quark fields, the gluon fields, the neutrino fields, the Higgs field, all of them are present, all of them fluctuating, all of them contributing their zero-point energy to the vacuum. You are immersed in a seething quantum ocean that you cannot see, cannot hear, cannot feel, but that is absolutely real and that shapes the physical world at the deepest level. This brings us to the deepest question. If empty space is filled with quantum fields, if those fields fluctuate constantly, if those fluctuations have real physical effects, what does this tell us about the nature of reality? What does it mean for the universe to be built from fields rather than particles? What does it mean for you, for everything you see around you, for the stars and galaxies and the vast dark spaces between them? Because the implications of quantum fields extend far beyond laboratory experiments and technical calculations. They change, in a fundamental way, what we understand the universe to be. We've arrived at the deepest layer of this story. We've seen that empty space is not empty. We've seen that quantum fields fill every point in the universe, that particles are excitations of those fields, and that even in the quietest possible state, these fields fluctuate with real, measurable consequences. Now it's time to step back and take in the full picture. Because what quantum field theory is really telling us is not just a technical fact about particle physics. It is telling us what the universe is made of. And the answer is unlike anything humans imagined for most of history. The universe is not a container holding objects. It is not a vast, empty stage on which matter performs. The universe is a tapestry of fields. Everything that exists, every particle, every force, every interaction, every atom in your body, and every photon from a distant star is a pattern woven into that tapestry. There is nothing else. Fields are all there is. Let that sink in for a moment. When you look around the room you're sitting in right now, you see solid objects. A table, a chair, a wall. They feel solid. They have weight. They resist your touch. They seem like definite, substantial things occupying definite positions in space. But at the deepest level of description that physics can currently provide, none of these objects are made of tiny, solid particles. They are made of field excitations, ripples in quantum fields that fill the room, that fill the building, that fill the planet, that fill the galaxy, that fill the observable universe, and presumably beyond. The table is a stable, self-reinforcing pattern of excitations in the electron field, the up quark field, the down quark field, and the gluon field, all interacting through excitations of the electromagnetic field, all given mass through their interaction with the Higgs field. Remove the fields and there is no table. There is no chair. There is no you. There is nothing. This is the worldview that emerges from the standard model of particle physics, the most thoroughly tested scientific theory ever constructed. It is not a hypothesis or a guess. It is the framework that has survived every experimental challenge thrown at it for over 50 years. Every time physicists have pushed their instruments to higher precision, every time they have probed smaller distances or higher energies, the quantum field picture has held up. Particles are excitations. Fields are fundamental. The vacuum is not empty. These are not speculations about what might be true. These are the established facts of modern physics. But let's explore what this means in more detail, because the implications reach into places you might not expect. Consider the space between galaxies. Intergalactic space is the most perfect vacuum in the known universe. In the vast voids between galaxy clusters, there is roughly 1 atom per cubic meter. By any everyday standard, this space is empty. There is nothing there. No planets, no stars, no dust, no gas. Nothing you could see or touch or detect with your senses. Just darkness stretching for millions of light years in every direction. But according to quantum field theory, this space is absolutely full. Every single quantum field in the standard model fills this space completely. The electron field is there, the photon field is there, the quark fields are there, the neutrino fields are there, the Higgs field is there. All of them, overlapping, coexisting, fluctuating quietly in their ground states. The space between galaxies is not void. It is the quantum vacuum, the ground state of a rich and complex system of interacting fields. It has energy, it has structure, it has physical properties that affect the behavior of anything passing through it. When a photon travels from a distant galaxy to your telescope, crossing billions of light years of apparently empty space, it is not travelling through nothing. It is travelling through the electromagnetic field, of which it is itself an excitation. It is also travelling through all the other quantum fields that fill that space. Those fields, even in their ground state, can affect the photon's journey in subtle ways. Vacuum polarization, a quantum effect in which the photon briefly creates virtual electron-positron pairs from the electron field as it travels, slightly modifies the photon's effective properties. This effect is real and has been measured in laboratory settings. The vacuum through which light travels is not an inert medium. It is an active participant in the physics of light propagation. Now consider something closer to home. Consider the interior of an atom. An atom is mostly empty space, we are often told. The nucleus is tiny, the electrons are far away, and in between there is nothing. This is a dramatic oversimplification. The space inside an atom is filled with quantum fields, just like every other region of space. The electromagnetic field fills the interior, carrying the force between the positively charged nucleus and the negatively charged electrons. The electron field fills the entire region, with the electron being a localized excitation of that field spread out in a probability cloud around the nucleus. Virtual photons are constantly being exchanged between the electron and the nucleus, mediating the electromagnetic force that holds the atom together. Virtual electron-positron pairs flicker in and out of existence in the space surrounding the nucleus, modifying the effective charge that the orbiting electron perceives. The interior of an atom is one of the busiest places in the universe at the quantum level. It is a constant storm of field excitations and virtual processes, all happening at timescales so short and distance scales so small that they are invisible to everyday experience. But they are not invisible to our instruments. They produce the Lamb shift, the anomalous magnetic moment, and dozens of other measurable effects that confirm the quantum field picture in exquisite detail. Let's talk about one particular field that deserves special attention because it plays a unique role in the story of empty space: the Higgs field. The Higgs field was proposed in 1964 by several physicists independently, including Peter Higgs, François Englert, and Robert Brout, among others. It was introduced to solve a specific problem in the Standard Model. The equations describing the weak nuclear force required the W and Z bosons, the particles that carry the weak force, to be massless. But experimentally, the W and Z bosons are very heavy, among the heaviest known fundamental particles. Massless particles travel at the speed of light and produce long-range forces. Massive particles travel slower and produce short-range forces. The weak force is short-range, so its carrier particles must be massive. But the mathematical structure of the theory seemed to forbid mass. Something had to give. The solution was the Higgs field. Unlike all the other quantum fields in the Standard Model, the Higgs field has a remarkable property. Its lowest energy state, its vacuum state, is not at zero field value. For every other field, the ground state corresponds to the field being at zero, with quantum fluctuations around zero. But the Higgs field's lowest energy state corresponds to a non-zero field value everywhere in space. The Higgs field, even in supposedly empty space, has a constant non-zero value permeating the entire universe. This is extraordinary. It means that even in the most perfect vacuum, even in the coldest, emptiest, most desolate region of space you can imagine, the Higgs field is not zero. It has a definite non-zero value, about 246 billion electron volts in the units physicists use. This value fills all of space uniformly. You are immersed in the Higgs field right now. Every atom in your body is bathed in it. Every point between here and the farthest galaxy is filled with it. The non-zero value of the Higgs field is what gives mass to the fundamental particles. Particles that interact with the Higgs field are slowed down by it, impeded in their motion, and this impedance is what we experience as mass. The more strongly a particle interacts with the Higgs field, the more mass it has. The top quark interacts very strongly and is extremely heavy. The electron interacts weakly and is very light. Photons don't interact with the Higgs field at all and are massless. Neutrinos interact incredibly weakly and have tiny but non-zero masses. Think about what this means. The mass of the electron, the property that determines how atoms behave, how chemistry works, how matter is structured, is not an intrinsic property of the electron itself. It arises from the electron field's interaction with the Higgs field. If the Higgs field somehow vanished from the universe, or if its value dropped to zero, electrons would become massless. They would travel at the speed of light. They could not be captured into orbits around nuclei. Atoms could not form. Chemistry would not exist. Matter as we know it would not exist. Life would be impossible. The very existence of atoms, of solid matter, of you, depends on the fact that the Higgs field has a non-zero value in supposedly empty space. Empty space is not just filled with fields, it is filled with a specific field configuration, a non-zero Higgs field, that makes the existence of matter possible. The vacuum is not nothing. The vacuum is the reason anything exists. In 2012, physicists at CERN confirmed the existence of the Higgs field by detecting its excitation, the Higgs boson, in proton-proton collisions at the Large Hadron Collider. The Higgs boson is the ripple in the Higgs field, just as a photon is a ripple in the electromagnetic field, or an electron is a ripple in the electron field. Detecting the Higgs boson confirmed that the Higgs field is real, that it fills all of space, and that it has the non-zero value that the Standard Model requires. But the Higgs field raises deep questions of its own. Why does it have a non-zero value? Why is that value what it is, 246 billion electron volts, and not some other number? The Standard Model doesn't answer these questions. It takes the Higgs field's properties as inputs, parameters that must be measured experimentally rather than derived from deeper principles. Many physicists believe that a more fundamental theory, perhaps one that incorporates quantum gravity or extra dimensions, or some entirely new framework, will eventually explain why the Higgs field behaves the way it does. But for now, we must accept it as a remarkable fact of nature. The vacuum of our universe has a built-in non-zero Higgs field that makes matter possible. Let me now turn to a broader perspective. We've been talking about quantum fields in the language of particle physics, focusing on the Standard Model and its mathematical framework. But the implications of the field picture extend far beyond particle physics. They touch on cosmology, on our understanding of the origin and fate of the universe, and on some of the deepest philosophical questions humans have ever asked. Consider the early universe. In the first moments after the Big Bang, the universe was incredibly hot and dense. The temperatures were so extreme that the quantum fields existed in very different states than they do today. At very high temperatures, the Higgs field's non-zero value is washed out by thermal fluctuations. Above a critical temperature of roughly 10 to the 15 degrees, the Higgs field averages to zero. In this state, all particles are massless. The W and Z bosons, the quarks, the electrons, all massless, all travelling at the speed of light, all fundamentally different from how they behave today. As the universe expanded and cooled, it crossed this critical temperature about 10 to the minus 12 seconds after the Big Bang. At that moment, the Higgs field underwent a phase transition, settling into its non-zero value throughout all of space. This is called electroweak symmetry breaking, and it was one of the most consequential events in the history of the cosmos. Before the transition, the electromagnetic force and the weak force were unified into a single electroweak force. After the transition, the Higgs field's non-zero value broke this symmetry, giving mass to the W and Z bosons, and splitting the unified force into the separate electromagnetic and weak forces we observe today. This phase transition is analogous to water freezing into ice. Liquid water is symmetric, it looks the same in every direction. But when it freezes, the water molecules arrange themselves into a crystal lattice that has preferred directions. The symmetry is broken. Similarly, before the Higgs transition, the electroweak force was symmetric, treating all its carrier particles equally. After the transition, the symmetry was broken. The W and Z bosons became heavy, and electromagnetism and the weak force became distinct. The entire structure of the physical world, the existence of atoms, the nature of chemistry, the possibility of complex matter and life, depends on this phase transition that happened within the first trillionth of a second of the universe's existence. It depends on the quantum fields and how they settled into their current configuration. The universe you see around you is the result of fields finding their ground state. There may have been other phase transitions even earlier. At even higher temperatures, the strong force may have been unified with the electroweak force in what physicists call a grand unified theory. If such unification occurred, there would have been a phase transition at roughly 10 to the minus 36 seconds after the Big Bang, when the grand unified symmetry broke, separating the strong force from the electroweak force. This transition might have driven cosmic inflation, the brief period of exponential expansion that is thought to have stretched microscopic quantum fluctuations into the large-scale structures we see in the universe today: the galaxies, the galaxy clusters, the filaments and voids of the cosmic web. If inflation really happened, and the evidence strongly suggests it did, then the largest structures in the observable universe, structures spanning billions of light years, originated as quantum fluctuations in fields during the first fraction of a second of the universe's existence. Tiny ripples in quantum fields, stretched to cosmic proportions by inflation, came the seeds around which matter later clumped to form galaxies and stars. The universe's entire structure, from the smallest atom to the largest supercluster of galaxies, is ultimately a story about quantum fields and what they do. Now let's consider the future. The current state of the Higgs field, with its non-zero value of 246 billion electron volts, might not be the true lowest energy state. It might be a metastable state, a local minimum of energy, rather than the absolute minimum. Imagine a ball sitting in a valley on a hillside. The valley is a local minimum. The ball is stable there. But farther down the hill, there might be a deeper valley. If the ball could somehow get over the ridge between the two valleys, it would roll down into the deeper one and settle at a lower energy. Some calculations, based on the measured mass of the Higgs boson and the top quark, suggest that the current vacuum might indeed be metastable. There might be a deeper, more stable vacuum state with a different Higgs field value. If this is the case, the universe could in principle undergo a catastrophic phase transition. A bubble of the true vacuum could form somewhere in space and expand outward at nearly the speed of light, converting everything it touches to the new vacuum state. Inside the bubble, the Higgs field would have a different value. The masses of all particles would change. Atoms as we know them could not exist. Chemistry would be different. Matter would reorganize into whatever configurations are possible with the new particle masses, which might be nothing recognizable. This is called vacuum decay, and it is one of the most dramatic scenarios in theoretical physics. If it happened, we would never see it coming. The bubble wall would approach at nearly the speed of light. No warning, no signal, no time to react. One moment, the laws of physics are what they are. The next moment, they are something completely different, and everything built on the old laws, including us, ceases to exist. Should you worry about this? Not really. Even if the current vacuum is metastable, the timescale for decay is estimated to be enormously long, far longer than the current age of the universe. The probability of vacuum decay happening in our observable universe within the next few billion years is incredibly small, but the fact that the possibility exists at all is remarkable. It tells us that the properties of the vacuum, the state of the quantum fields in empty space, are not fixed forever. They could change. The very fabric of reality as we know it depends on the vacuum being in a particular state, and that state might not be permanent. This underscores a point that runs through everything we've discussed tonight. The vacuum is not passive. It is not a backdrop. It is not a stage on which the drama of physics plays out. The vacuum is part of the drama. The state of the quantum fields in empty space determines the rules of the game. It determines which particles exist, what masses they have, what forces act between them, and what kinds of matter can form. Change the vacuum state, and you change everything. Let's bring this home to something personal. You are made of quantum field excitations. Every electron in your body is a ripple in the electron field. Every quark in your protons and neutrons is a ripple in a quark field. The forces holding your atoms together are mediated by photons, which are ripples in the electromagnetic field. The nuclear force binding your nuclei is carried by gluons, ripples in the gluon fields. And the masses of all your particles, the property that gives your body weight, arise from the interaction of these fields with the Higgs field, which permeates all of space at a constant non-zero value. You are not separate from the fields. You are the fields. You are a particular arrangement, a particular pattern, an incredibly complex and beautiful configuration of quantum field excitations that has persisted for decades, maintaining itself through constant interactions, constantly exchanging virtual particles with the vacuum, constantly participating in the quantum activity that fills all of space. When you move your hand, field excitations rearrange. When you think a thought, field excitations propagate through your neurons. When you die, the excitations don't disappear, they dissipate. The energy returns to the fields in other forms, as heat, as radiation, as simpler configurations of matter that eventually recycle into new patterns. This is not a metaphor. This is what the equations of the Standard Model describe. You are a localized, temporary, self-organizing pattern in a system of quantum fields that fills the universe. You emerged from the fields, and you will return to them. The fields themselves persist. They were here before you were born. They will be here after you are gone. They were here before the earth formed, before the sun ignited, before the Milky Way coalesced from clouds of gas and dark matter. They will be here after all the stars burn out, after the galaxies drift apart, after the universe grows cold and dark. The fields are eternal, in a sense that nothing else is. Stars are born and die. Galaxies form and disperse. Even the protons and neutrons in your body might eventually decay over timescales of 10 to the 34 years or longer. But the fields themselves, the electron field, the electromagnetic field, the quark fields, the Higgs field, these endure. They are the permanent infrastructure of reality. Everything else is temporary excitation. This brings us to one of the most profound shifts in how we understand the universe. For most of human history, people thought of matter as the fundamental stuff. The world is made of things, objects, substances, atoms in the original Greek sense of indivisible building blocks. Space was merely the arena in which these things existed, the container that held them. Matter was real. Space was empty. The story of physics was the story of how matter behaved. Quantum field theory inverts this picture entirely. Space is not empty. Space is the physical entity, or rather, the fields that fill space are the physical entities. Matter is not fundamental. Matter is what the fields do. The story of physics is not the story of how objects move through a void. It is the story of how fields fluctuate, interact, and excite each other, producing the transient patterns we call particles, atoms, molecules, planets, stars, and living beings. This is arguably the most important conceptual revolution in the history of physics, more fundamental even than relativity or quantum mechanics themselves, because it redefines what exists. It replaces objects with processes. It replaces things with patterns. It replaces permanence with dynamism. The universe is not a collection of things. It is a field, or rather, a system of fields, constantly in motion, constantly fluctuating, constantly creating and destroying patterns of excitation. And the most remarkable thing about all of this is that you are part of it. You are not an outside observer looking at the universe from some detached vantage point. You are the universe observing itself. You are quantum fields, organized into a configuration complex enough to be aware of its own existence, to ask questions about its own nature, to develop mathematics precise enough to describe itself with 12-digit accuracy. When you look up at the night sky and see the stars, you are quantum field excitations, looking at other quantum field excitations across a vast expanse of quantum fields in their ground state. The light entering your eyes is a stream of photon excitations in the electromagnetic field, generated by nuclear processes in distant stars where quark and gluon field excitations fuse and release energy. That light travelled through the quantum vacuum for years or centuries, crossing regions filled with fluctuating fields, before being absorbed by electron field excitations in the atoms of your retina, triggering a cascade of chemical and electrical signals that are themselves patterns of field excitations propagating through your nervous system. At every stage, from the nuclear furnace of the star to the neurons in your brain, the story is the same. Fields excite, fields interact, fields transfer energy, fields create patterns. That is all that happens in the universe.